This is the simplest multiple choice question. PH.D.S. Also because of this problem, scratching their heads, writer be besieged by 1,000 people. This is the famous three-door problem. Let's review today. This is a hugely controversial issue. Look at you, smart. Can you make the right choice? Imagine a game where you have 3 doors in front of you. Behind a door is a sports car. Behind the other 2 doors are goats. The host asks you to choose a door. You chose door 1. Then the host started to mess things up. He opened door number 2. Let you see with your own eyes a goat behind the door. Then he smiles and asks you now. Give you a chance. You can change to door 3. You can also stick to your original choice. How do you choose? What would you do at this point? The vast majority of people's first reaction is not to change. It's purely mental behind this. And those who calm down, people who try to analyze logically, and I came to the conclusion that it was always the same. Is it 50/50ths? After all, there are only 2 doors left. Who knows which door the car is behind? Is that really the case? In fact, the best strategy is to switch. It's that simple act. It can directly double your chances of winning the car. This is known as the Monty Hall problem. You may find this bizarre. That's right, it's already been a challenge for mathematicians. Completely solved problem. And the answer has been repeatedly verified. But to this day, he can still confuse countless people. Even flip the table. The more the usual explanations say, it confuses the skeptics. In this video, I'm going to take you through it. Why is that? The name Monty Hall problem. This is from the 1960s. It's the ultimate TV show. Let's Make a Deal. And his host, Monty Hall, is on the show. Contestants also choose one of 3 doors. There is a grand prize behind the door. There are also some worthless gadgets. Sometimes it's a goat. But the rules of the game are not rigid at the beginning. Mengti is wily. He sometimes won't let you change the door. I'll give you a sum of money directly to let you go. Sometimes for show effect. He will also deliberately engage in some psychological The real tipping point came in 1990. A woman named Marilyn, the women writers of Worth Savant, in his column, presented a pure version of the game. In this version, the rules are drying out. Host will always open a door with goats, and will always give you the opportunity to change the door. His conclusion was like a bomb. Changing doors can directly pull your winning rate from 1/3 to 2/3. This is a hornet's nest. Professor Mathematician Street, a student, wrote to him. Fierce accusations that he was wrong. Some people, even if you slap a mathematical proof in his face, he couldn't believe it. After all, the Monty Hall problem. It's a head-to-head collision of intuition and logic. As soon as we heard about this game, it's easy to bring in. I began to wonder if this host was tricking me. Is he trying to trick me into replacing the correct door? These ideas are too normal, but it strays from the heart of the problem. The mathematics behind this problem don't care about any intrigue at all. I don't care if you believe him or not. Here's the thing. Remove all human distractions. Just look at the probability. Only so we can see the truth behind the numbers. In reality, thinking about the human heart may be important, but to unravel this backstory, you've got to figure it out mathematically. To do this, you must first accept the following iron laws. 3 doors and 1 car. 2 sheep. You choose a host first. Man opens another door with sheep. You get a chance to change doors. In this game, the host is a programmed robot. To make you feel more at ease, we could even add another rule. If the host has 2 sheep to choose from, he can choose the smaller one. You flip a coin. This rule doesn't affect probability. Just to make you stop wondering why he opened the door, don't open that fan. To put it bluntly, the most crucial information is 1. The host knows where the car is, and he will always help you rule out a wrong answer. This is the secret to making money by changing the door. You just have to accept the premise. And then the mathematics sort of falls into place. To make you feel this more intuitively, let's have a big game. This is Marilyn, the writer. Brilliant explanation. It's called 100 doors, 99 goats. And the idea is to radicalize the scene. Once the scale is expanded, the logic behind changing doors becomes very clear, at least in theory. Imagine that. There are 100 doors in front of you. Behind a door is a brand new sports car. Behind 99 doors are all goats. The host asks you to choose a fan. You shout, "I choose door 1." And now the show begins. The host knows the inside story. 98 doors have been opened since door 2. All goats without exception. But there's a strange place. He only jumped through gate 29. Now there are only 2 gold doors left in the field. Your original choice of door 1 and the gate 29 specially left by the host. He asked your friend if he would change it or not. What should you do then? I guess the vast majority of people now will choose to change it without hesitation. What do you think in 99 doors? He just left this one. This move is too deliberate. Something tells you there's a ghost at door 29. That's right, you're straight. I think it's right this time. Changing doors is an absolutely wise choice. Because of your face, something big has happened. But you know why in the case of 100 doors? Is your intuition that accurate? And it's very simple. When you choose door 1, the probability of choosing the right one is only the probability that the car is in the remaining 99 doors. The host's door opening performance doesn't change your initial 1% probability. All he did was take that huge 99% probability, concentrate in the remaining doors. When he rules out 98 wrong answers for you, all 99% of the time, they all converged on the only door he left behind, on door 29. So your winning rate is 99%. Insist on not changing. Your winning percentage is still that poor 1%. However, this explanation is shocking, but there is a small problem. He needs you to take a mental leap. The insights gained from 100 doors apply back to the scene of 3 doors. A lot of people get stuck here. Why is that? Because the 100 doors example is your attention is focused on 99%. Attractive. It's easy to think that gate 29 is the chosen one. But the principle by which this game really works, it's the host who uses his information to help you troubleshoot. Because a shift in probability. It's exactly the same in 3 doors and 100 doors. So here's the challenge. How to make people aware. No matter how many doors there are, mathematical logic doesn't change. This hurdle cannot be passed. The explanation of the 100 doors. Another story. It's not a bigger version of the same question. So to really understand this backstory, the key is not the number of doors, it's the behavior of the host. How did you revolutionize the distribution of probability? This is the core of the door-changing strategy. Of course, yeah. If you think of the thought experiment above, still a little winding. Then let's take the dumbest and most practical method, the exhaustive method. We break down all possible scenarios, crushed and placed on the table. Let you see clearly. When you list all the possibilities, the pattern can't be hidden. Suppose your head iron chooses door 1 then there are 3 situations in total. The car is chose at number 1. The host will open number 2 or 3. If you don't change it, you win the car at gate 2. You chose number 1. The host must open number 3. If you change to no 2, you win the car at gate 3. You chose number 1. The host must open number 2. If you change to no 3, you win. Do you understand? Only 1/3 of the time. No exchange can win. That is, you get lucky when you go out. When you get it right the first time. And in the remaining 2/3 cases, you can win by changing doors because the car is in the 2 doors you didn't choose. It's pretty amazing. There was hardly any room for argument. Changing the door is more torn. However, even if the evidence is so conclusive, some people are still not convinced. Why is that? Because although this table proves that changing doors can win, but he didn't answer the gut question. Why open a door? Isn't the probability 50-50? People are stuck on this hurdle. I always feel like the host's behavior resets the game, although mathematics tells us otherwise. Exhaustive only shows what it is, without explaining why this is the case. This lack of explanation, let the skeptics always feel. Did you miss any key link? Let's think of it another way. You can think of this game as your choice. A showdown with all the remaining options. This perspective can help you clear your mind in an instant because he emphasized, change door. It is equal to the probability that you put all the unselected doors packed. After you choose the door you chose has a car. The probability is 1/3. And the remaining 2 doors, they hide as a whole. The total probability of the car is 2/3. Is that okay? Here comes the host. He's from the 2 remaining doors you didn't choose. Picked a wrong option for you. His move. It doesn't affect your original 1/3 probability, but he left that 2/3 probability unchanged. All transferred into that hole, on the only remaining door. So, if you made up your mind from the beginning to change, it's like you're betting. I'm stuck in traffic and it's not in the door and in the remaining door, because the host always will help you eliminate a distraction. So your door switching strategy let you steadily inherit the 2/3 merger probability. This is the essence of changing doors for better. It's not a random choice between two doors at all. Instead, you take advantage of the host's informational advantage. Higher merger probability for nothing. This is a rather counterintuitive explanation. We are used to putting every door as an independent entity, make you believe in changing a door. That's the probability of getting to doors. It's like playing with words. After all, there is only one door left. How can he represent the probability of two doors? This is the cognitively hardest curve to turn. It is also difficult for many people to see through. The fundamental logic behind this. If you think the above explanation is not rigorous enough, it's the ultimate statistician's favorite weapon, Bayesian inference. This method, I will calculate all the details clearly. Keep up with this idea. You have to accept a core idea first. Probability is not static. It has to be updated as new information becomes available. And Bayes' theorem is the correct posture for doing this. We don't have to look at complicated formulas. Look directly at the app. Suppose you choose door 1. The host opened door number 3. It's a goat now. We have to calculate. After the host opens door number 3, after this new information emerged, what is the probability of door 2 on the car? To get results, we need 3 key probability values. If the car is really at gate 2, what is the probability that the host will open door 3? The answer is 100%. Because you chose no. Car number 2. He tried not to let you see the car. You can't open door 1 you chose, so he can only open door 3. He had no choice without knowing anything. What is the initial probability that the car is at gate 2? The answer is 1/3. This is the bright probability at the beginning without knowing anything. What is the total probability that the host will open door 3? The answer is 1/2. Because if the car is at gate 1, he can take a half chance on no 2 or no 3. If the car is at gate 2, he has to drive number 3. If the car is at gate 3, he can't drive number 3. Put it together. The overall probability of him opening door number 3 when we bring these 3 values into Bayes' theorem, the result is 2/3. This means that the probability that the car is behind the door is 2/3. In other words, changing doors is a smart move. You might want to ask, what about the probability that the car is in gate 1 of my choice? Let's do the math in the same way. The only difference is that the first person knows if the car is really at gate 1. What is the probability that the host will open door 3? The answer is 1/2. Because the car is behind the door he can be between number 2 and choose number 3. Anyone to open. Bring this value into the calculation. The result obtained is 1/3. The calculation results tell you clearly the door you originally chose. The probability is always 1/3. To really understand this paragraph, and the best way to do that is to actually do the math. When you go through the numbers yourself, you will be convinced to see what changing doors can give you a higher chance of winning. You know what? The real difficulty of the Munting Hall problem is not in the mathematics. He challenged our deep-rooted thinking instincts. He forced us to question perceptions that seem natural. For example, about fairness and randomness. When the host opens a door, we instinctively feel the remaining 2 options are equal opportunity. It feels fair. Matches our sense of symmetry. 2 doors, 1 car, 55 open. But this back theory, it just reveals a deeper truth. Probability is not static. The emergence of new information will change even if nothing has changed in the physical world. And here's what's even worse. And this shift in probability is not visible to the naked eye. The host just opened a door. It didn't increase or decrease anything. He just told us something. Things we didn't know. However, it is this revealing action, like an invisible hand, redistributing the probabilities, put a greater possibility pushed into the door you didn't choose. This subtle shift is extremely counterintuitive because he doesn't meet our daily processing of random events. We always want the rest of the options to be equal because it's simple and fair. For those who can believe in abstraction, for those who focus on mathematics, the answer is simple: change the door. Win rate to thirds does not change. Win rate 1/3 math doesn't lie. But for those who are obsessed with the storyline, I always feel that the host's just an accident. For those who reset the game, no matter how you interpret the answer, it doesn't feel right. They focus on the story itself, rather than the probability behind it, and the result is that the cogs of logic never get right. But this apocryphal is about more than just a game. In fact, it is one of the most common ways a microcosm in the face of problems. We rely on experience and intuition, but in some cases, it's our intuition that misleads us. The Monty Hall problem tells us to see things that are not so intuitive. Tools of abstraction, simplification, and mathematical reasoning. It's all about conditional probability. Emergence of new information. How to fundamentally change the possibilities of things. This principle applies in reality to statistics. Areas like financial decision-making are ubiquitous. Emergence of new data necessarily requires us to reassess our past judgments. Monty's game. It can be said to be a contraction of countless challenges in our lives. Whether making decisions based on incomplete information or manage risk, interpreting the data, we will always meet when intuition and logic fight. In these moments, choose to believe in math and underlying logic often leads us to better outcomes. Even if he didn't feel right at first. That is to say, trust logic over intuition can bring better returns. For example, you choose to arrange a 1-arrow 3 company for Lal Ma now.